We want to find the position vector function r of t for a particle with acceleration, initial velocity, and initial position given below. So we're given the acceleration vector valued function, the velocity vector at t equals 0, and the position vector at t equals 0. So if we take a look at this graphically, our ultimate goal is to find r of t that would trace out this purple space curve, and we're given the position vector at t equals 0, this light green vector here, and we're also given the velocity vector at t equals 0, which would be this red vector. This dark blue vector here is the acceleration vector at t equals 0, which we could find since we're given a of t. And we can find the position vector function r of t by using integration. Since we're given the acceleration vector valued function, we'll first find the velocity vector valued function by taking the integral of a of t, and then we can find the position vector function r of t by finding the integral of v of t. So we'll first find v of t, which is equal to the integral of a of t, and we're given a of t, so we have the integral of the vector valued function with an x component of 2t, a y component of 2 sine t, and a z component of cosine 4t. And now we'll integrate each component with respect to t. So the x component would be the antiderivative of 2t, which would be 2 times t squared divided by 2, or just t squared, plus a constant, which we'll call c sub 1. The y component would be the antiderivative of 2 sine t, which would be negative 2 cosine t, plus, let's call it c sub 2. And the z component would be the antiderivative of cosine 4t, which does require u substitution. U equals 4t, differential u equals 4 dt. So if we divide both sides by 4, notice how 1/4 du equals dt, which means we'll have an extra factor of 1/4 when integrating. So the antiderivative of cosine 4t is going to be 1/4 sine 4t plus, let's call it c sub 3. And now because we're given the velocity vector v of 0, we can determine the constants of integration. So if v of 0 equals the vector 1, negative 3, 2, if we substitute t equals 0 into the x component, notice how we would have 0 squared plus c sub 1 must equal 1. Again, 0 squared plus c sub 1 must equal 1. Therefore, c sub 1 equals 1. Looking at the y component, if we substitute 0 for t, cosine 0 is equal to 1. So we'd have negative 2 times 1, or negative 2, plus c sub 2 equals negative 3. Adding 2 to both sides, we know that c sub 2 equals negative 1. And then finally, for the z component, when t equals 0, notice how we'd have sine 0, which is 0. So we'd have c sub 3 equals 2. Which means now we know that v of t has an x component of t squared plus 1, a y component of negative 2 cosine t minus 1, and a z component of 1/4 sine 4t plus 2. And now that we have v of t, we can integrate to find our position vector function r of t. Let's do this on the next slide. So now r of t is equal to the integral of v of t, which we just found. So we'll have the integral of, again, the x component is t squared plus 1, the y component is negative 2 cosine t minus 1, and the z component is 1/4 sine 4t plus 2. And once again, we'll find the antiderivative of the x, y, and z components. So for the x component, we'd have t to the third divided by 3 plus t plus a constant, which we'll call c sub 4. For the y component, the antiderivative of negative 2 cosine t is going to be negative 2 sine t. The antiderivative of 1 is t, so minus t plus c sub 5. And now for the z component, notice how again we have to perform u substitution, where u equals 4t. So we'll have an extra factor of 1/4 again. And since 1/4 times 1/4 is 1/16, the antiderivative of 1/4 sine 4t would be negative 1/16 cosine 4t. And then I have plus 2t, and then plus c sub 6. So if you need to, you can go back and take a look at the u substitution when we found v of t. And now because we're given r of 0, we can determine the constants c sub 4, c sub 5, and c sub 6, which will give us our position vector function r of t. Again, we know that r of 0 has an x component of 2, a y component of 4, and a z component of negative 1. So we'll substitute t equals 0 into each component to determine our constants. So if we substitute t equals 0 into the x component, we'd have 0 plus c sub 4, which must equal 2. So we know c sub 4 equals 2. Looking at the y component, if t is 0, we have sine 0 here, which is 0. So we have 0 minus 0 plus c sub 5, which must equal 4. So c sub 5 equals 4. And finally, looking at the z component, this one's a little bit more involved. When t is 0, we have cosine 0, which is 1. So we'd have the equation negative 1/16 plus 2 times 0, which is 0, plus c sub 6, which must equal negative 1. So if we add 1/16 to both sides, we'd have c sub 6 equals negative 1 or negative 1 over 1 plus 1/16. Well, of course, negative 1 is equivalent to negative 16/16, and therefore c sub 6 equals negative 15/16. So finally, now we know our position vector function r of t has an x component of, let's say, 1/3 t to the third plus t plus c sub 4, which we know is 2, so plus 2. The y component is negative 2 sine t minus t plus c sub 5, which is 4, so plus 4, and a z component of negative 1/16 cosine 4t plus 2t plus c sub 6, which would be negative 15/16 or minus 15/16. So quite a long process, but from the given information, we were able to determine the position vector function r of t that once again would trace out the purple space curve that we see here. I hope you found this helpful.